We'll pick up where we left off and then move on to the learning portion. But just to review, where we left off was a solution concept, say that with some model of what's going to happen. And the model that we're working with now is Nash Equilibrium. And as we said, the Nash Equilibrium says that everyone's choice is optimal with respect to what everyone else did. So again, if all of us were at a Nash Equilibrium, we would go out of the room one at a time and say, this is what others did, this is what you did, do you want to change? And if everyone says no, we're at a Nash Equilibrium. Nobody's better off by changing their choice. By the way, it's unilateral. Unilateral is an important part of Nash Equilibrium. Two people could be better off by simultaneously changing their choices. Okay, but Nash Equilibrium is silent about that. It's unilateral analysis. Now, to talk about Nash Equilibrium, it's convenient to introduce the so-called best response function. And the best response function is what is your optimal reply to what others are doing. Okay, and it's using this notation. So A minus I means the actions of everyone else except for agent I. And so what is the best response of agent I to the actions of everyone else? A minus I, what everyone else is doing. And in fact, that it's a set-valued function. There can be multiple best responses. And let's look at the best response function in action, and it will help us construct Nash equilibria. But this is another way to write Nash equilibria. The action that I've chosen is a best response to the actions that everyone else has chosen. So in simple cases, let's construct the best response. This was the hawk-dove game. And let's see, what's the best response for the row player? This is the best response function. If the column player plays H, the row player has a choice between these two numbers. Bigger is better. So the best response to H is D. Okay? If the column player plays D, the row player has a choice between 4 and 1. The best response is 4. And therefore, we can illustrate the best response function here. 0 means that D was the best response to H, and it's red here. So H was the best response to D. This is the best response function. We just built the best response function for the row player. Now let's build the best response function for the column player. And it turns out to be symmetric. So the best response, let's see, what's the best response to H? They're picking between -1 and 0. 0 is better, so they'll pick D. What's the best response to D? They're picking between 4 and 1. 4 is better. And now we have a best response map completely mapped out. So based on this color system, where's the Nash equilibrium? The Nash equilibrium is when each one is playing a best response to the other. So any cell that is all red, that's going to be a Nash equilibrium. We see here that this game happens to have 2 Nash equilibria, okay? And it's a symmetric case, so one player is passive and the other player is aggressive, and either way, column or row. So what we did here is we used the best response map to build a Nash equilibrium. So now we can start just using this best response map to start building Nash equilibria in general. And here's prisoner's dilemma. Let's build the best response for the row player. If the column player plays C, cooperate, they're picking between 2 and 3. 3 is better. So that's the best response. If they pick D for defect, 0 and 1, 1 is the best response. So this is the best response map. Likewise for the column player, and here then is the Nash equilibrium. The Nash equilibrium is 1, 1. Okay? This, by the way, is what's known as a dominant strategy. Generally, best response is sensitive to what the other person does. Should I play H or D? Well, it depends on what the other person is playing. Look what happened in prisoner's dilemma. Should I play C or D? I don't care what they're playing, D is better. So D dominates C. No matter what they're doing, D is better. Okay. I don't know if you used that when you picked D or you just wanted to betray me. Okay. Now, this is not a Nash equilibrium. Remember what we said? 2 players can change both moves simultaneously and simultaneously be better off. Doesn't matter. Nash equilibrium is only about unilateral changes, not combined changes. And that's part of the interest of the prisoner's dilemma. There's a long story that goes with that. Okay, stag hunt, these are the two Nash equilibria, and you can go through it and build it yourself. So both go for deer or both go for rabbit. Okay, matching pennies. This game's called Matching Pennies, and we'll talk more about it in a moment, but let's see. This happens to be a zero-sum game, and the story is that the row player wants to match, and the column player wants to mismatch. Okay? What's an analogy? Like penalty kicks. The goalie wants to match the side that the striker strikes, whereas the striker wants to mismatch. They want to go to the opposite direction. The best response to heads is heads for the row player. The best response to tails is tails for the row player. They're trying to match, but the column player is trying to mismatch, so this game doesn't have a Nash equilibrium. So we can have a unique Nash equilibrium, multiple Nash equilibria, or no Nash equilibria. All of these are possible outcomes of a game. Okay, this is the comfort game. The story behind this game is that there's a seat on, there's some room on the train, and I prefer sitting to standing, but I don't like sitting next to someone else because it's not as comfortable. Okay. And you can assign all of these. Let's see, my favorite thing is, I'm the row player, my favorite thing is to sit while the other person is standing. My second favorite thing is to sit while the other person is sitting, but it's not as comfortable. And then if I'm standing, I don't care what the other person's doing. Okay? And again, one can go through the best responses and find out that both of us sitting down is the Nash equilibrium of this game. More interesting variation is what I'll call the etiquette game. In the etiquette game, I like sitting instead of standing, but I find it rude to sit when the other person is standing. Okay? And what happens here, if you look at that situation, what's the Nash equilibrium? We both end up standing and not taking the seat. And this is, I mean, this is a nice fable out of this, or moral out of this fable, that etiquette is not done correctly unless everybody's inconvenienced. Okay? We can have more involved settings. Okay, for example, this is a contribution game, and the contribution is as follows. There's something that will be provided to all of us, provided that enough of us pitch in. Okay, so we need exactly K or more to pitch in. Okay, so and then our preferences are as follows. The best thing for me is that the good is provided and I didn't pitch in. The second best thing for me is the good is provided and I pitched in. The next best thing is the good is not provided, and we're missing some, yeah, the good is not provided, but I didn't pitch in. And the worst thing is the good is not provided and I had committed. Okay, that's the worst thing. It turns out that one can go through the analysis and find out that there's two Nash equilibria to this. One Nash equilibrium is when exactly K people pitch in. And the other Nash equilibrium is that nobody pitched in. Okay, zero. So the good is not provided, but nobody pitched in. When there's exactly K, then we can go and ask those that pitched in, would you like to withdraw? Those that didn't pitch in, would you like to pitch in? And you can just do the analysis and find out that that's the Nash equilibrium, that exactly the right number pitch in. So, you know, I have here a variety of settings with a variety of Nash equilibria. For example, there's this so-called second bid, sealed bid second price auction and the like. I'm just going to skip all of this stuff and let's go back to matching pennies. So you get the idea. You can build up Nash equilibria. It can be in simple settings. It can be in more complicated settings. Let's build our way towards slightly more complicated setting. We said that this didn't have a Nash equilibrium, right? So what are the elements of a game? There's a set of players. We have two players here. They have choices. Okay, what is their choices here? Left, right, or left, right? I change it from heads, tails to left, right. And then there's a consequence or preferences over joint choices. And this didn't have a Nash equilibrium. But now let's redefine the setting. Instead of my choice as left or right, let me make my choice probability of left and probability of right. Okay, I'm changing my choice. The probability of left and probability of right. So now, whereas my choice set just had two elements, now my choice set is the unit interval from 0 to 1. Okay, and that's going to be my probability of left, and of course my probability of right is 1 minus left. All right. And so I'm redefining the choice set. So now what did we have? Who are the players? Row and column. What are the choices? Probabilities. probability of left and probability of right. We're not done yet. We said the game has a number of players, a group of players, a choice, and then consequences, how they evaluate their choices. And what we're going to do is we're going to introduce this expected utility. So how I value probabilities is what is the expected utility depending on our choices. So now that we changed the setting, we're back in the original setting. What's the original setting? I need a group of players, a choice set, and how they evaluate choices, joint choices. What's the set of players? Rows and columns. What is their choices? Probabilities. How do they evaluate probabilities? Through expected score, in this case, okay? And now that we modified the setting, now that we modified the setting, it turns out that this does have a Nash equilibrium. And can anyone guess what the Nash equilibrium is? It's what's half-half, yeah, half-half. If anything is slightly more than half, then the other player can take advantage of it. And so then what happens is that when they go half-half, then the player becomes indifferent. If the person is going 50-50, if I go left, if I go right, I get the same expected score. If I go any combination of the two, I get the same expected score. So it turns out that by doing this, looking at so-called mixed strategies, the game that didn't have a Nash equilibrium now has a Nash equilibrium. And in fact, that's the famous Nash result, that all finite games where the players have a finite number of strategies and expected utilities, they always have a Nash equilibrium. So there's always a Nash equilibrium when we consider expected utilities with probabilities, or so-called mixed strategies. A mixed strategy is the probability of taking an action as opposed to the actual action. And then there's the proof uses fixed point theory. So we can build the best response map to Hawk-Dove. Some of the numbers changed a little bit here. And the best response map actually looks like this. My best response, I'm building the best response to the opponent. The opponent has a probability now of playing a dove or hawk. So what does it mean when my best response is 1? That means that I'm going to pick a certain action with certainty. When my best response is 0, I'm going to pick the other action with certainty. What does this thing mean? What's my best response? My best response is pick any probability, it doesn't matter, okay, because I'm indifferent. And then the other player, we can build their best response map, and this has, now remember where's the Nash equilibrium? When each is a best response to the other. And we see that there are 1, 2, 3 Nash equilibria. What are the Nash equilibria? There were the pure ones. We recapture the pure ones, but we found a new Nash equilibrium, and that's when both players mix. When both players mix, there's a third Nash equilibrium in this game. Now, back to the question of, how sophisticated can the setting be? Let me just talk about one particular kind of formulation that just gives a reflection of how complicated this can be. I'm showing here a bunch of 2x2 matrices, but it can be a lot more involved. So we're motivated here by a security situation where one player has more information than the other player. There's a user and then there's an attacker. The user, say, has more information than the attacker. And there's a tension that comes up in that if I have superior information, then if I take advantage of my superior information, the attacker can improve their information and learn to attack me. So then we call this exploitation versus revelation. So here's a particular instance. I'm the user. I have 4 different channels. Okay? One channel is a high capacity channel, and the other channels are low capacity. What's going to happen is that over the course of a few days, I'm going to use my network. But then at the end of the week, let's say, the attacker kills one of my channels, destroys one of my channels. And now I have to use whatever's left. So the question to you is, what would you do? You're interested in throughput. So you're incentivized to use the high capacity channel during the week. But what's the downside of that? The downside of that is that by using the high capacity channel, the attacker might say, oh, they're using that channel a lot. I'm going to disable that channel, and now you have to live with the remainder of the network for the remainder of the time, whatever that remainder of the time is. So that's the tension. Do I use it or not? Okay? And one can formulate this as a game. And in fact, the optimal strategy for the user is to use a particular channel with certain probabilities, and those probabilities depend on what channels they used in the past. So day one, I'm going to flip a coin, and that's going to determine what channel I use. And then when I see what channel I used, that's going to change the probabilities of the coin that I flip on day two. And then so on. And that turns out to be the optimal strategy to confuse the attacker, to play randomly, but not uniformly randomly. So let's look at the extremes. The extreme is use one of the four uniformly at random. Then I'm not using the information that I have. The other extreme is use my good channel, in which case the attacker knows what my good channel. I've betrayed my superior information. The blend in the middle is use my good channel with certain probabilities, and one can kind of construct these probabilities, and those probabilities evolve as a function of how, what channel I've been using in the past. So I'll just skip over this, and this gives a kind of a numerical construction of what I just talked about. So this is, again, an instance, though, of that we've been talking about. It looks like a bunch of 2x2 matrices, everything happening at once, but it can happen over stages with more sophisticated settings. And so now we'll move to the second part of the talk. And the learning question. Okay. So we have the definition of a game. We have a suggested model of an outcome. The suggested model is Nash Equilibrium, and it's not without controversy that we have a Nash Equilibrium. Now let's revisit the beauty contest, and we kind of talked about this at the closing of the first lecture. The Nash Equilibrium, as you've all noted, is that everybody selects 0, but that didn't happen. Okay. By the way, this portion of the talk was put in advance. It didn't happen. Okay. It wasn't now, oh, I noticed it didn't happen, so I'm going to type. No, it didn't happen. You know why it didn't happen? Because it never happens. All right. Also, 0.001 never happened. Okay. But it didn't happen. All right. So why should we believe in Nash Equilibrium when it didn't happen? And in fact, this is an issue that has been kind of bugging game theorists for a while. Here's one quote from a book on game theory. Game theory lacks a general and convincing argument that a Nash outcome will occur. Now, there are certain special cases, which I really didn't talk about much, but in zero-sum games, I'm not really worried about am I in equilibrium. I just want to protect myself, and I don't care about what the other person does. I'm guarding against the worst case. And when both players guard against the worst case, it happens to be a Nash equilibrium. That's one case. And now dominant strategies, Nash equilibria emerge in dominant strategies. You remember the definition of a dominant strategy? I don't care what they're doing, because no matter what they do, defect is the best. Okay, so in those kind of very special cases, Nash equilibria emerges, but there's different issues. Empirical evidence, we had our own empirical evidence today that a Nash equilibrium didn't emerge. There may be multiple Nash equilibria, and if that's the case, which one do we believe in? And there's also the computational complexity, and there's lots of negative results on what does it take to even compute a Nash equilibrium. And it turns out that in general, it doesn't scale very well. Okay, so why should we believe in Nash equilibrium as the outcome of two human players, where the computational complexity is such that it's not reasonable to assume that a computer can compute a Nash equilibrium having all information? Okay, so there are kind of issues associated with Nash equilibria as a solution concept. But now this is the data that I was referring to when at the end of the last lecture. This is the repeated beauty contest. And let's look at, let's see. These are the selected numbers between 0 and 100 in the first round. And you see there's a cluster at 50. There's another kind of cluster at 25, a bigger cluster at 13. Now, somebody said 100. There's always, There's always a jerk in the audience. All right. So this clustering is informative, okay? But also what's informative is that if we plot the fourth, and these plots are coming from this paper that appeared in 1995. If we plot what were their choices in the fourth period versus the third period, this line, being below this line, means they picked a smaller number in the fourth period than they picked in the third period. Okay? And you see that almost everybody, first of all, we're moving towards zero, and almost everybody's fourth round choice is smaller than their third round choice. So we see that there is a unraveling, a drifting towards the Nash equilibrium. So maybe Nash equilibrium could be viewed as a nice model when people have repeatedly played the game. Okay? And in fact, that is what the literature of so-called learning in games is all about. Okay? It's repeated play. And so now we're not going to talk about what's the Nash equilibrium. We're going to talk about how players might arrive to a Nash equilibrium. Now, in other words, dynamics. And so this, for us in this audience, this should be very curious that Nash equilibrium, well, if you said what's an equilibrium, yes? Yes.
So in this case, there was just one Nash equilibrium, but if there are more than one, then this learning, is it going to converge, or is...
So there can be all of the above. It doesn't converge. It converges to one of them indifferently, or there's a preference to one over the other, and the preference can be expressed in different ways. Okay, yeah, all of the above. But my point right now is that if we said, if I asked you what's the equilibrium, what's your first question? Okay, well, what were the dynamics? You start with dynamics and say what's the equilibrium of the dynamics, right? Nash equilibrium, we started with the equilibrium. And now we're going to, so usually we start with the dynamics and say, what's the equilibrium? We started with the equilibrium and we're going to say, what's the dynamics? Okay, the dynamics have not been specified. And so I want to highlight this word might, how players might arrive to an equilibrium. This is not necessarily a model of how players do arrive to an equilibrium, but just a plausibility argument, okay? And so as with plausibility arguments, we want dynamics that are well motivated. And these are two nice quotes that reflect the spirit of the learning in games literature. One is, the attainment of equilibrium requires a disequilibrium process. Before we even talk about equilibrium, we need dynamics. That's the disequilibrium process. Another is, the explanatory significance of equilibrium depends on the underlying dynamics. If we're going to believe in an equilibrium outcome, well, we need to believe in some dynamics that took us there. So it's going to be about learning, and we're here. What I want to say in this slide is that the learning story is a bit more subtle than we might otherwise believe, even if we have a good background, say in adaptive control or in learning control, and for the following reason. The premise of learning is as follows, okay? If I do an experiment today and I do the same experiment tomorrow, then the results are going to be the same. Maybe there's some statistical variations, but the results are the same. The outcome is the same. Why? Because I'm learning in a stationary environment. So over time, by doing various experiments, I can figure out how to best engage the environment and then figure out what's the best thing to do in the long run. But that requires a stationary environment, okay? Now, what does it mean to have multi-agent learning? I'm doing experiment today. What's the environment? Other learners. Other learners. So as I'm trying to figure you out, you're trying to figure me out. So from any one agent's perspective, the environment is not stationary. Why is that? Because I'm experimenting on you and you're experimenting on me. Okay? And so weird things can happen when you have interacting learners. And we'll illustrate that with this simple learning rule. It's called reinforcement learning, and it's as follows. I have a bunch of choices. Every time I take a choice, I get some reward. I take a reward. If I did choice number 2, I put that reward in bucket number 2. If I did choice number 7, I put the reward in bucket number 7. So now I have this vector of rewards. Okay? What am I going to do tomorrow? Well, I'm going to pick not necessarily the choice that gave me the maximum rewards. I'm going to use these buckets to determine what probability I take tomorrow's choice, the probability of tomorrow's choice. What's been working well, I choose with higher probability than what has been working well. So the biggest bucket is going to be the most likely action, but I still can take the other actions with different probabilities. Okay, this is so-called reinforcement learning. The probability of taking an action is proportional to the accumulated rewards that I've experienced taking that action. And this is now a video of rock, paper, scissors. Okay, it's not a video of a bunch of hands, but rather it's a video of the probability of rock, the probability of papers, and the probability of scissors. So this is the probability simplex. This means rock, this means paper, this means scissors. Right in the middle is 1/3, 1/3, 1/3, which means equal probability. And what we're doing is we're plotting reinforcement learning when both players are playing reinforcement learning against the other. Okay, but before we plot this, suppose your opponent played rock more than they played paper and scissors, and they were fixed. What do you think reinforcement learning would do over time? Eventually it would learn to play paper. Not immediately, because it could be that it slightly favored rock. But over the long run, paper is working better, and over the long run it's going to converge to paper. Now when both players are playing reinforcement learning, this is the probabilities of one of the players. And it looks chaotic. And in fact, there's a paper that says mathematically this is chaotic. Okay, so two players playing rock, paper, scissors, both of them doing reinforcement learning against each other, can lead to chaotic outcomes. So that makes the point that learning amongst learners is, a subtle thing. Okay, it's because, again, there is no stationary environment. The environment with respect to one learner is the other learners, and everybody's moving. Okay?
Sorry. I
Yes.
didn't get the point of the example. So,
Mhm.
so in this example, did you bias one of the players towards playing more rock?
No. So if one of the players, that was just the intro. If one of the players was biased to rock more, then the person's going to. But no, they were both reinforcement learners, and they were both equal opportunity reinforcement learners, and they ended up chasing each other. Okay, so we're going to look at different kind of learning rules. And a learning rule, you can think of a learning rule as just what's the probability that I choose my next action based on the information that I have that I choose to use. Okay, the information available that I choose to use. This is the simplest learning rule possible. Okay, this is called best reply with some inertia. So my choice today is a best response to what others did yesterday. That's it. So, like they say, respond to the most recent crisis. Right? This is what others did yesterday. I'm going to react optimally with respect to that today. And then just repeat. And we gave it a little bit of inertia. I'm going to do that with certain probability, but every now and then I'm lazy and I just do what I did yesterday. Okay? So best reply to what others did yesterday, or and just do what I did yesterday. Okay? So you can think of this as, well, let's see. If we're playing in this way, if we happen to start at a Nash equilibrium, we'll stay at a Nash equilibrium. Why is that? Because I'm best responding, and we were already best responding. So if we start there, we stay there. We can think of this as I'm making a forecast about what you're about to do, and I'm going to best respond to that forecast. This is not a sophisticated forecast. What is the forecast? I forecast you to do what you just did. Okay, and I'm going to do a best response. And you can construct different cases where it does not converge to a Nash equilibrium, but there's a special class of games where these simple dynamics do converge. In general, they need not converge, but there's a simple class of dynamics where they do converge. There's something called finite improvement property games. I'm going to say what that means in a moment. Okay, finite improvement property games converge to Nash equilibrium. And to do that, we need a particular construction called the better reply graph. So the better reply graph, an arrow, a node means a joint action. And an arrow means somebody can improve their utility through a unilateral change. So here's what the better reply graph might look like if I had, let's see, if I had 3 players 2 actions each. 3 players, 2 actions each. So we could all be playing, I think my actions are 0 or 1. We could all be playing zeros. We could all be playing 1 or anything in between. That's our configurations. What does this arrow mean? This means that player 2 can realize an improvement by switching from 0 to 1. Okay? And each of these arrows means that an individual player, who's the player that realizes an improvement in this case? The third player. Boom, 1, 2, 3, the third player. What does it mean when there are no outgoing arrows? We're at a Nash equilibrium. No individual player can realize an improvement. How come we don't have an arrow from 000 to 111? Because it's only unilateral moves. We're looking at one at a time changes. What's special about the finite improvement property is that this directed graph always terminates. If this directed graph always terminates, then the best response dynamics that we just put up will converge. Why is that? Because everyone's doing a better reply. There may be simultaneous better replies. Oh, but now you see what inertia does. Inertia means every now and then it's going to be one person replying. And that's enough to lead it to a Nash equilibrium. Okay? Now, yes?
You ruled out simultaneous replies, but they may happen in fact. Right?
They may happen. So the way the proof works is you construct a series of fortunate events. Because of the inertia, yes, simultaneous replies might happen, but individual replies might happen as well. And if you have enough individual replies in sequence, then you'll hit a Nash equilibrium. But that's not a guaranteed outcome. It happens with positive probability. So with probability 1, it'll eventually happen. That's the nature of it. Okay. It can't infinitely be avoided.
Why don't we have an arrow from 011 to 111?
From 011 to 111. And the way this was drawn, there's no outgoing arrow here. That means that this is a Nash equilibrium. There's no outgoing arrow at all.
Mm-hmm.
Okay. Okay. So it turns out that this is the best reply path for graph for stag hunt, and it has 2 Nash equilibria. This is the better reply path for matching pennies, and it doesn't have any Nash equilibrium. It cycles. Okay. So it looks like we have a property of a game. If the property has this finite improvement, if the game has this finite improvement property, then we know we have some dynamics that will work. Now let's look at the following game. This is called a congestion game. We want to go from A to B. Let's say there's R different roads. The congestion on a road depends on the number of users of that road. And to make things simple, everybody experiences congestion in the same way. Congestion is bad for all of us. It's not that I like to take the scenic route, and it only depends on the number of the users, not on their type. So a moped and a truck cause the same amount of congestion. Okay, we'll simplify it that way. Now this is an anonymous congestion game, and let's see how many configurations are there. Suppose we have 10 roads and 100 users. Okay, how many different configurations are there? There's going to be 10 to the 100 different configurations. There's no way we're building the better reply graph for this graph, okay, for this game. So can we find a proxy, so a certificate that this game has the better reply property, the finite improvement property, even though we can't build the graph, okay? And it turns out that there is a special class of games for which you can have a certificate that this has the finite improvement property without building the graph, okay? And this special class of games are called congestion, are potential games. Yes? So for potential games, let's see. A game is a potential game if there exists a particular function that is not player dependent that has the following property. the change in utility for an individual deviator equals the change in this potential function. Okay? The change in utility for an individual deviator equals the change in the potential function. Now, let's try to build some insight into that. Let's see. If we have a potential game, can there be a cycle of best responses? Like this has a cycle of best responses. Suppose this were a potential game. All right? Then, what happened here? The individual improved, so therefore the potential function goes up. A different individual improved, the potential function goes up. A different individual improved, the potential function goes up. Can we come back to where we started through improvements? No. You can't have the potential function growing and be back to where you started. So if a game happens to be a potential game, then the better reply graph can't have cycles. And if it doesn't have cycles, it has to terminate. Okay, so if somehow we can figure out that a game is a potential game, then we'll know that it has this finite improvement property, and then we'll be guaranteed that best response dynamics converge.
So if you have no cycle, it is a potential.
No. It's not if and only if. Yeah. I mean, you can think that there's lots of weakening of this. So one weakening, you see this equal sign.
Yes.
Another weakening would be it just has the same sign. Up means up, down means down, but not this equality. Another weakening is if this is an improvement, that's an improvement. So just you don't even need sign equality. You need just that when this is positive, that's positive. That would be enough to get the finite improvement property, in fact. So the potential is very strong of an assumption. It turns out that congestion games are potential games. That game that would have had 10 to the 100 nodes to build a better reply graph, this is the potential function. One can construct this potential function. And the potential function is not overall congestion. It's something else. But through this, one can verify that this works as a potential function. Now, you might think that we need to be pretty lucky to get a potential game, and you would be right to say that. But in the next lecture, we're going to show that, well, since we're using game theory to design systems, we'll cook the books so that our game is a potential game. We're the ones who designed the game, so we'll make the game a potential game through a clever construction. All right, so we have one approach to learning a pure Nash equilibrium, but we have to luck out and have the finite improvement property. And then there's a whole host of other learning rules, and let me try to mention two of them briefly. All right, how would we learn mixed strategy? Turns out there's a very famous or well-known another learning rule that's called fictitious play. So let's see, with best reply, what did we do? I looked at what you did yesterday, and I used that as a forecast. With fictitious play, I'm going to be a little bit more sophisticated. I'm going to keep a histogram of what you've done. Okay, so suppose you're allowed to go left, middle, right. We've played for 100 days, 30 days you went left, 30 days you went middle, 40 days you went right. I'm going to take that histogram and say my prediction from you tomorrow is 0.3, 0.3, 0.4 in probability. I'm going to use the histogram as a forecast. It's not really how you're behaving, but that's how I'm going to model you. Okay? So my guess about what you're about to do is the histogram of what you've done. Whereas in best response dynamics, my guess about what you're about to do is what you just did. Okay, so it's a little bit more sophisticated. And it turns out that fictitious play converges in zero-sum games. It converges in potential games. It converges in any 2x2 game. And there's a handful of other games where fictitious play converges. But there's also a handful of games where it's known not to converge. And what's interesting is that a potential that fictitious play can converge to a mixed equilibrium. So here's rock, paper, scissors. The equilibrium of rock, paper, scissors is 1/3, 1/3, 1/3. And here's a simulation showing fictitious play converging to 1/3, 1/3, 1/3. Here's fictitious play applied to the congestion game. By the way, what do you think a Nash equilibrium is in the congestion game? There's a bunch of roads, and we want every player to be happy with the road that they took. So what's going to be the congestion on all of the roads? The same, yeah. And that in the traffic literature is called a wardrobe equilibrium. And here the players are playing fictitious play, and in the limit, the congestion on all of the roads is the same, which means that they're at a Nash equilibrium. And I'll give you one more learning rule, which is a pretty amazing one, actually. And the next rule we're going to talk about is so-called no-regret dynamics. Okay? No-regret dynamics says the following. Suppose I have two choices and I'm interacting with an environment. I can look at the past and say, what would have happened if I had played left every day? And the other person did the same thing, that actually did what they did, okay? What would have happened if I had played right every day and the other person had the same history, okay? So here I'm deciding, whether or not to bring an umbrella or sun lotion, and that was what the weather actually did, okay? So when it rained, I should have brought an umbrella. When it rained, I should have brought an umbrella. But what I actually did, let's say in this case, the red is what I actually did. So I have regret when I did the wrong thing, okay? So the regret is what would have my score have been had I done a particular action versus what my score was realized. That's my regret. And if a regret is positive, what does that mean? For example, suppose regret is positive for umbrella. That means my cumulative score would have been better had I brought the umbrella every day. If my regret is positive for sunscreen, my cumulative score would have been better had I brought sunscreen every day, based on the history that I just recorded. Okay? So this is the so-called regret vector. And no regret learning, there's a whole family of no regret learning, but this is one type of no regret learning. Let me take the vector of regret for each of my actions. Remember, if it's positive, that means I wish I did that instead, based on the history that I just recorded. Keep the positive ones and play probabilistically with respect to positive regret. Okay, so if my regret was 10, -3, 4, get rid of -3 because I don't have regret. 10, 0, 4. Then I'm going to play the first action with probability 10 divided by 14. The last action with probability 4 divided by 14. You take your regret vector, get rid of the negative elements, and normalize it so that it's a probability vector. And what's amazing about no regret learning is that you're guaranteed, we're not talking about Nash equilibrium here, you're guaranteed to have no regret as time goes on. All right, it's pretty striking. So my average regret goes to 0. And it turns out, if both players play no regret learning, it does converge to a particular equilibrium, but a kind of equilibrium that we haven't talked about. There's Nash equilibrium, then there's something called correlated equilibrium, and it converges to correlated equilibrium. And it's universal. I think I'm out of time. All I'm going to say about this is that it addresses the question that you raised. What if there's multiple Nash equilibria? And there's a family of learning rules that balance, exploit versus explore. They'll do a best response with high probability, but they'll explore with low probability. It turns out that the mathematics behind that is such that through exploit versus explore, the dynamics will be going all over the place, but it tends to stay at Nash equilibria for a long time. And it stays at some Nash equilibria longer than others. So stochastic learning rules can favor different equilibria. It turns out that if you did best response with an occasional error on these dynamics, it'll spend most of its time here at the safe Nash equilibrium. It'll move all over the place, but it'll spend most of its time there. And that's it for this lecture. Okay, so let's see. We have Nash equilibrium, but we now shifted the attention to learning. We looked at best reply, we looked at fictitious play, we looked at no regret, and I just barely mentioned this at the very last minute of if we use stochastic dynamics, they can differentiate between different equilibria and favor some over others. Okay. All right, that's it for this lecture. Thank you.
So for many games you have scores for different actions, and how do you obtain such scores in social applications or in engineering applications?
In engineering applications, we can cook them, okay? Because we're the ones who, these are our players, our devices, and we can incentivize them. And so tomorrow we'll be talking about how what are good ways to incentivize our sensors or our whatever it is that we're building. In the social case, it's there's a lot of work on. Well, remember, in the social case, we're not necessarily looking at the number in a quantitative way, but more as a qualitative way. What are preferences, and what happens as this thing gets large and as that thing gets small? But we're not looking to actually populate. We will populate it with numbers, but we don't take those numbers too seriously. They just reflect preferences. And then we can ask questions like, what happens as the preference gets much stronger for one thing over another? So that's looking at kind of relative comparisons, which is different from what happens when this utility equals 7, and then what's the outcome? Generally, they don't ask those kind of questions.
I have the impression that in these learning techniques, you assume that all players adopt the same learning strategy? Or
Generally, that assumption is made for convenience. Now, in the no regret learning, you can show unilaterally that the player using no regret learning will asymptotically have 0 regret, regardless of what the others are doing, regardless. Okay, so that's a unilateral guarantee. There is some interest in when they're heterogeneous learning rules, but for convenience, most of the time people assume that all of the players are using the same learning rule.
I was thinking in the case of playing against the environment, or the environment, I mean, it doesn't have a particular utility, then maybe it's just doing random choices. Well, if you have try to model
Okay.
an enemy, then maybe it's trying to cause as much damage to you.
So the nature of these learning rules are such that if the environment is statistically stationary, then over the long run, it'll be optimal with respect to that environment, because they all have that kind of best response feature. They're looking to climb uphill. So against that stationary environment, it'll find the maybe a local maximum, but it'll find the peak. Against a non-stationary or a malicious environment, then you look for unilateral guarantees. So it turns out that the zero-sum case can be addressed. It's when it's not necessarily zero-sum that you get this chasing. Like the rock, paper, scissors I showed, that's chaos. That's chaos with reinforcement learning. But if you applied fictitious play to rock, paper, scissors, it converges to the equilibrium very nicely. So the next lecture will be about how can we take these learning rules and modify them to an engineered system. So now it's not a plausibility argument of how agents might reach Nash equilibrium, but rather it's an online learning device to cause a bunch of agents to do something that we want them to do. Yes?
The numbers you presented us were they were covering the areas
Mhm.
and applied some of these.
It's using a learning rule that I didn't show you yet. Okay, but it's exactly this. We're going to do two things. We're going to incentivize the agents so that we have a potential game. Okay, and then and the potential game will guarantee this finite improvement property. And then we're going to introduce exploration in a particular way so that the agents maximize coverage in the long run. Yeah, but it's a learning rule that I haven't told you yet.
It was really interesting that you mentioned that reinforcement learning in this paper just as an example, didn't do as well as what was the name of the strategy?
Fictitious play? Yeah.
Fictitious play,
Yeah.
that's right. Even though fictitious play seems really simple, it's just using the best estimator for the probabilities if
Mhm.
they're stationary.
Mhm.
And then the other one is supposedly more sophisticated. Is there something that you could say to?
Well, I would push back on when you say it didn't do as well. I mean, that you know, at this level, there's no, you know, if something cycles versus chaotic versus converges, so what? Because because there was actually I showed this one example. This is a painful story for me to recreate.
So you talked about stability, but you didn't talk about the payoff.
Well, yes, so that it could be that cycling leads to higher average payoff than convergence. So
Thank you.
this was the so-called Shapley game, and the Shapley game, fictitious play cycles in the Shapley game. Now this game also has a unique mixed equilibrium where it's 1/3, 1/3, 1/3. It's not a zero-sum game, but it turns out that when they cycle, their cumulative reward is higher than had they converged to a Nash equilibrium. So it could be that cycling from the perspective of welfare is better than convergence. Yeah.
Very cool. Thank you.
Thanks.
Any other questions?
All right. Thank you very much, Jeff.
Okay, thanks.